This is an example of a two-dimensional surface that we did. The voltage is on the vertical axis, and the position is on the plane on the bottom. There is a x-axis along here, there's a y-axis along here, and this is color-coded. So the height along here gives us the equipotential surfaces for this particular geometry, which looks like a pair of T's facing each other. It's the two-dimensional analog of the two plates. The equipotential surfaces are these intersections of the multicolored regions, and the electric field is perpendicular to those. So the electric field points in this direction. I like these three-dimensional representations because they enable us to think of this as an electrical hill, if you will. And positive charges would have a tendency to roll down or glide down by always moving perpendicular to the intersections between the planes. So we can think of the potential as the electrical analog of height in terms of gravity. And I always like to, in my head, run a little cartoon of a positron on skis skiing down these slopes. They're trying to pick up the greatest amount of speed as they get to the bottom, so they're always looking at the steepest rate of change. We have arbitrarily, through the use of our multimeter, set V equal to 0 at the bottom. And this one appears to have a maximum V of about 4.2. This is 2 points. So we see this curving behavior here, very similar to what one would expect from a dipole. So if you look at the greatest steepness going from this high peak, which is around 3 volts, down to this low peak, which we have assigned to be apparently 0. Very characteristic looking dipole field. The line down the middle is straight, giving us a very characteristic straight line operation. And if you were to graph that one line alone, you would end up linearly, and you would be able to do a direct calculation of the electric field strength. Only along this line, though, you would have to actually do some pretty elaborate analysis to get the rate of change along the other lines. This last one that we're going to look at is 1 point in a plane. And if you look at this, this curves around and goes into this flat. We have arbitrarily, again, assigned our 0 here at the bottom. And this shows us what that looks like. And this one is interesting because it gives us the sort of half field from 2 points. So you can imagine we could put the other half of this. So this is from the high down to 0, and we could do another one from the 0 down to some negative point, and it would look exactly like the previous 2 points.